Hello everyone, this is Maushmi. Today I am here to clarify some of your doubts on moving charges and magnetism. Hope you are following us at Aptdemy and going through our online as well as offline videos. To remind you all, we have been putting in a lot of free videos from time to time. So please do see the videos and subscribe the channel. So the first doubt that we received from the students is the one on magnetic induction. This is basically related to the Biot-Savart's law. We have already covered the theory portion in our videos. Now let me read out the question. Find the magnetic induction of the field at the point O if a current carrying wire has the shape as shown in figures A, B and C. The radius of the curved part of the wire is capital R. The linear parts are assumed to be very long. Now, as you can see, there are three different figures. Each of these figures have straight conductors in the form of KL and MN, and there is a curved portion in each of these figures. For the first part, the curved portion is LM. For the second figure, it's again LM, but the shape is a bit different. And for the third part, again, it is a semicircular arc LM. Now we are to find out the magnetic induction at the point O for each of these three figures. Now let us first recall the Biot-Savart's law. Now the Biot-Savart's law basically tells us that the magnetic induction at a point due to a straight conductor is given as B, and B is equal to mu naught by 4 pi I vector dl cross vector r by r. Now, here mu naught is the magnetic permeability, I is the current flowing through the wire, r, dl is the line element, and r the distance. Now, applying this formula to the first figure, we are trying to solve out for the figure A initially. Now for figure A, when we see the magnetic induction at the point O due to the conductors KL and MN, the magnetic induction at O due to KL and MN. Now look at the figure. KL and MN both are in line with the point O at which we are to find out the magnetic induction. So it's verified that the angle made in each of these cases is equal to 0 degree. So if we directly apply the formula for magnetic induction due to a straight conductor. Now magnetic induction at a point due to straight conductor. The formula is actually mu naught I by 4 pi r sine of phi 1 plus sine of phi 2. Now keeping an eye on this formula, what are the angles phi 1 and phi 2? Now phi 1 and phi 2 are basically the angles made with the line element or with the ends of the straight conductor corresponding to the point at which we are finding out the magnetic induction. So as we can compare this formula with the figure, we see that in each of these cases, phi 1 and phi 2 both are equal to 0 degree. So we can see that sine 0 plus sine 0 amounts to 0 multiplied with this factor mu naught I by 4 pi r, which will give us the magnetic induction at O due to KL and MN as equal to 0. So we see that magnetic induction at O due to the paths Lm, Kl and Mn both are equal to 0. Now what is left out? We are left out to find out the magnetic induction at O due to the curved portion Lm. Let's work that out. Magnetic induction at O due to circular, it's actually semicircular, due to the circular part Lm is. Now look at the figure. We have to find out the magnetic induction at O due to this semicircular part. So taking this formula in mind, let us move forward. We have the magnetic induction as mu naught times I by 4 pi. Let's take, this is R cube. So let's do R cube here. Now what is dl and r for this part? Now dl is the length of the path. As the path is semicircular, the length of this path is half the perimeter. That is, we can say the circumference. So half the circumference is nothing but pi times the radius. So radius is r here. We have the length element as pi r. So we have pi r coming out from the length element. Now we are left with r. What is r here? It's capital R actually. Small r is equal to capital R. We have r square coming out. Now what is the angle in this case? We can see that the angle here is 90 degree and sine 90 is equal to 1. So ultimately here we get sine 90 degree which is equal to 1. So this amounts to mu naught I pi r square will get cancelled out with the denominator and we are left with 4r in the denominator. So what is the net magnetic induction? The net magnetic induction at O is, for the parts KL and MN, we have zeros coming up, and for the curved portion, we have mu naught I by 4r coming up. So finally, we see that for the figure A, the net magnetic induction at the point O amounts to mu naught I by 4r. Now let us follow a similar procedure for the other figures, that is for the figure B and for the figure C. Now, proceeding in the similar manner, let's have a look at the figure B. Now, if you take a look at figure B, we are thinking of the same formulas here. The magnetic induction as per Biot-Savart's law is mu naught by 4 pi times I d vector dl cross vector r by r cube, and the magnetic induction at the point O due to the element Kl. Now see, the distance of the conductor Kl from the point O at which we have to find out the magnetic induction, the distance is nothing but equal to the radius, that's r. So we shall apply the same formula that we have for magnetic induction due to a straight conductor. In this case, how the formula gets modified to, let's work on that. We have mu naught I by 4 pi r and sine phi 1 plus sine phi 2. What will this amount to? Now, if you take a look at the ends of the conductor here, for the particular end L, the angle made is 90 degree, while for the end K, the angle made is very small and can be neglected or can be assumed to be 0. So if we take a look at the sum of this, we have 1 plus 0 coming up. Ultimately, the magnetic induction at the point O due to the element Kl is nothing but equal to mu naught I by 4 pi r. Now, here the point is actually in line with the conductor Mn. So, if they are in line, we can consider the case as before, that is the angle in this case will be equal to 0 degree. So, we have magnetic induction due to Mn as equal to 0. Now, looking at the curved portion, what is the magnetic induction due to the circular portion? Magnetic induction due to the circular portion. That's Ln. So let's try and apply the formula here. We have mu naught I by 4 pi r cubed coming up. Now, looking at dl and r here. What's dl in this case? If you take a note, this is more than a semicircle, or you can see that it is almost 3/4 of a circle. Now, this is nothing but half the circle is equal to pi r, plus we have pi by 2 r coming up. That is pi r by 2 for this particular portion. That is how you can see for this particular portion, the length or distance covered is pi r by 2, and for the remaining semicircular portion, the distance coming up is nothing but pi r. So this gives us the net line element, that is the value of dl, as pi r plus pi r by 2. So if we are doing this, we do pi r plus pi r by 2, we get it as 3 pi r by 2. So we have this as 3 pi r by 2. And we have another r coming up. So we have r square over here. Now if we cancel out the common terms, this will amount to 3 mu naught pi I. You can see this as 3 mu naught I by, this is 8 r. So this is 3 mu naught I by 8 r. Now, again, going back to the net magnetic induction at the point O due to the figure B. So the net magnetic induction is nothing but equal to sum of the 3 magnetic inductions that we have calculated for each of the parts separately. So we have the net magnetic induction at the point O due to figure B coming up as, this is one part of it, that is mu naught I by 4 pi r, plus we have a 0, plus we have 3 mu naught I by 8 r coming up. At the end, we may write it as the net magnetic induction at O due to figure B. The value may be written as B equals, this is mu naught I by 4 pi r, and we have 1 plus 3 pi by 2 coming up. So we can very well solve this out. This is the net magnetic induction at O due to the figure B. Now, switching over to the figure C, let's have a look at that. Magnetic induction at the point O. We are doing this for the figure C. Due to KL and Mn is. Now, if you take a look at the diagram, you can see that Kl and Mn both are straight conductors and both of them are at equal distances from the point O. That is, the distance is equal to r in each case. And what's the angle in each of the cases? As you can see that from the point O, the angle for each of these straight conductors will be equal to 90 degrees. So proceeding on that note, we have the magnetic field induction at point O due to Kl and Mn. Applying this particular formula, we get this as mu naught I by 4 pi r. We can see that one of the angles is 90 while the other will be 0. So we get the magnetic induction due to these two elements as equal to mu naught I by 4 pi r. Now, going further with this, if we try to find out the magnetic induction at the same point O due to the curved portion Lm. Magnetic induction at O due to the circular part Lm. Now, for the circular part, as we can see, we have this. We should apply the same formula, the second one over here, Biot-Savart's law. We have this as mu naught I by 4 pi r cube. Now, working on dl cross r. As you can see, it's semicircular path. So dl will be equal to pi r multiplied by another r. So we have pi r squared here. And the angle is 90 degree and sine 90 amounts to 1. So this is the thing that results. Ultimately, we can write this as mu naught I by 4 r. So we have mu naught I by 4 r coming up. Now, again, finding out the net magnetic induction. Since for these two terms, for the two parts Kl and Mn, we have the same term coming up twice, and we shall add that to mu naught I by 4 r. So the net magnetic induction at O due to figure C is, let's go on, look at the first term. We have mu naught I by 4 pi r. For the second one, we have it as mu naught I by 4 r. This is the circular part. And for the third part, again, it's a repetition of the first one. We have mu naught I by 4 pi r. So ultimately, we get it as mu naught I by 4 r may be taken as common. We are left with, this is 1 by pi plus 1 by pi, that's 2 by pi, plus we have a 1 coming up. So this is the net magnetic induction at point O due to the figure C. So hopefully your doubts are clear. See you soon with more videos. Keep posting your doubts and we shall clarify them in these online sessions. Thank you. Now, moving on to another similar doubt that you had put forward. We are here with magnetism and matter. Let's look on the doubt and try to solve it. A thin insulated wire forms a plane spiral of n equals 100 type turns carrying a current I equals 8 milliampere. The radii of inside and outside turns shown in figure are equal to A equals 50 millimeter and B equals 100 millimeter. Find the magnetic induction at the center of the spiral and the magnetic moment of the spiral with a given current. So this is the diagram of the spiral. As you can see, the spiral is nothing but concentric circular coils. The internal and external radii are different. Suppose they vary from R and R plus dr. You can assume that. And the radii are given as A equal 50 millimeters and B equal 100 millimeters. We have a current of 8 milliampere passing through the spiral. So let us first recall the magnetic induction at a point due to a circular coil. The magnetic induction at a point due to a circular coil. Let's take it as B, and B is equal to, let us take it as dB, small amount. So dB is equal to mu naught I by 2R, where R is the radius of the circular coil and I is the current flowing through the coil. Now when we are talking of a circular coil, we are actually considering a coil of a single turn. That is, N is equal to 1 for this particular case. Now moving forward, a plane spiral is actually nothing but made up of concentric circular coils with radii varying from R to R plus dr. So this is the variation in radii. We are of course given the internal and the external radii in this case. So proceeding forward, the net magnetic induction. The net magnetic induction at the center of the spiral. Now, what we can write this as? Let us write the net magnetic induction as B. This is nothing but an integration of this amount of magnetic field, of course, taking into consideration the total number of turns. We need to take in the total number of turns which are there in the spiral within the interval R and R plus dr. So looking at this, B is nothing but integration of dB, and we have to take into concern here the value of dn, where what is dn? dn is the total number of turns of spiral in the interval R and R plus dr. No. Now the other thing that we need to note here is how do we write the value of dn? Now, dn, what is dn? We have said that dn is the total number of turns. Now, a single turn, if you consider the circular coil of single turn as n, then the number of turns actually, the internal and external radii actually varies from A to B. So, we have to consider the turns in such a way. So, this is actually, dn is actually equal to n by, this is B minus A. B is the external radii and A the internal one. So this is equal to n by b minus a, and the variation in radius or the interval of radius within which we can define dn is nothing but equal to dr. So let's now proceed with this value of dn in the original formula and continue the calculation. So we have b equals, this is integration dv, which is mu naught I by 2r. We have dn substituted as n by b minus a times dr. Now what are the limits of this integration? Of course, the limits are a to b, a being the internal and b the external radii. So let's take the constant terms out of the integration sign. We have mu naught ni by 2 times b minus a coming out of the integration. And finally, within the integration, we are left with dr by r. So we can see that integration of dr by r is nothing but log r, of course, with the base e. So we may write b as equal to mu naught ni by 2 times b minus a, and this is log r times base e, sorry. Then we may write mu naught ni by 2 times b minus a. Now we still are yet to put the limits of the integration. So let's do that. We have r first, we need to put the upper limit. So we have log b minus log a. Now log b minus log a may be written as log of b by a. So we write this as log b by a, of course, with the base e. So if we now proceed with the values, we can very well arrive at a numerical value at the end of this. So we have mu naught, we know the value of mu naught. It's nothing but 4 pi times 10 to the power minus 7 in SI units. We have n given as 100. We have I as 8 milliampere. Let's convert that to ampere. It's 8 times 10 to the power minus 3 whole divided by 2 times b minus a. Let's use the SI units. B is 100, A is 50. So we have 100 minus 50, and millimeters converted to meter has a factor 10 to the power minus 3 multiplied with it. And then we are left with log. We have b by a here. B is 100 and A is 50. So we have 100 by 50, that's 2. So we have log 2 base E basically. Now when we put in all the values and we calculate this, we amount at a value of magnetic induction at the center of the spiral, B being equal to 7 times 10 to the power minus 6. This is the numerical value. And since we have done the problem in SI units, so we will arrive at the SI unit of magnetic induction, which is Tesla. So this is how we proceed for the first part of the problem. Now, keeping an eye on the remaining part of the question, we need to find out the magnetic moment of the spiral with a given current. So, magnetic moment. Now, if we consider the circular coil with a single turn, say, that is for a single loop, what is the magnetic moment, or how do we write the magnetic moment in that case? So, magnetic moment for one loop, specifically, it is one loop, we may write the magnetic moment as equal to, we have the current multiplied with the area. Now for a single circular loop or a single turn of the circular coil, the area is nothing but equal to pi r square, where r is the radius of the circular coil. Now when we need to write down the magnetic moment for the spiral. It is written as integration of that for one loop, that's I times pi r square, and we need to multiply that with the total number of terms, which is dn. Now, just substitute the value of dn, give proper limits to it, and solve it to get the net magnetic moment. So, the limits are a to b, we have I, pi, r square, and dn is n by b minus a times dr. So this is the thing which we arrive at. Let's take out the constant terms. We get this as n I pi by b minus a and integration of r square dr. The limits are a to b. Now recall, integration x to the power n dx is equal to x to the power n plus 1 by n plus 1. So when we have r squared here, we have the value of n as 2. So solving this further, we get this as ni pi by b minus a, and this is r cubed by 3. And the limits are yet to be put, a to b. So the net magnetic moment may be written as ni pi by, we have b minus a, and we have a 3 coming out. Now, look at this. We have r cube and we need to put in the limits. So we put the upper limit first, that is b. We have b cube minus a cube. So working on this further, we know that this amounts to b cube minus a cube may be written as b minus a times b square plus a square plus ab. So we see that b minus a gets cancelled out, finally giving the net magnetic moment as ni pi by 3 times b square plus a square plus ab. So now we need to put in the values. N is 100, I is 8 times 10 to the power minus 3 in SI units. We have pi as 3.142 by 3 times. We need to put the values of A and B. So putting in the SI units, B square, that's 100 times 10 to the power minus 3 whole square of that, plus A square, which is 50 times 10 to the power minus 3, again whole square of that, plus AB. So we have that as 50 times 100, that's 5000, times 10 to the power minus 3 whole square, which is 10 to the power minus 6. So finally we can solve this and get a numerical value for the net magnetic moment, and the answer that you get here will have the SI units, which is ampere meter square. So work this out further and get the result, and you have the unit as ampere meter square. So thank you all for posting on your clarifications. We shall be bringing up more solutions for you. So keep posting and stay tuned with Aptdemy. Thank you.